Hysteresis is the time-based dependence of a system's output on present and past inputs. The dependence arises because the history affects the value of an internal state. To predict its future outputs, either its internal state or its history must be known. If a given input alternately increases and decreases, a typical mark of hysteresis is that the output forms a loop as in the figure. Such loops may occur purely because of a dynamic lag between input and output. This effect disappears as the input changes more slowly. This effect meets the description of hysteresis given above, but is often referred to as rate-dependent hysteresis to distinguish it from hysteresis with a more durable memory effect. Hysteresis occurs in ferromagnetic materials and ferroelectric materials, as well as in the deformation of some materials in response to a varying force. In natural systems, hysteresis is often associated with irreversible thermodynamic change. Many artificial systems are designed to have hysteresis. For example, in thermostats and Schmidt triggers, the principle of hysteresis is applied to avoid unwanted frequent switching. Hysteresis has been identified in many other fields, including economics and biology, etymology and history. The term hysteresis is derived from sigma tau epsilon rho eta sigma iota sigma, an ancient Greek word meaning deficiency or lagging behind. It was coined around 1890 by Sir James Alfred Ewing to describe the behavior of magnetic materials. Some early work on describing hysteresis in mechanical systems was performed by James Clerk Maxwell. Subsequently, hysteretic models have received significant attention in the works of Ferenc Prysak, Lewis N. Acute L. and D. H. Everett in connection with magnetism and absorption. A more formal mathematical theory of systems with hysteresis was developed in the 1970s by a group of Russian mathematicians led by Mark Krasnozelsky. He suggested an investigation of hysteresis phenomena using the theory of nonlinear operators. In engineering, control systems. In control systems, hysteresis can be used to filter signals so that the output reacts less rapidly than it otherwise would, by taking recent history into account. For example, a thermostat controlling a heater may switch the heater on when the temperature drops below A, but not turn it off until the temperature rises above B. Similarly, a pressure switch can be designed to exhibit hysteresis with pressure set points substituted for temperature thresholds. Electronic circuits often, some amount of hysteresis is intentionally added to an electronic circuit to prevent unwanted rapid switching. This and similar techniques are used to compensate for contact bounce in switches, or noise in an electrical signal. A Schmidt trigger is a simple electronic circuit that exhibits this property. A latching relay uses a solenoid to actuate a ratcheting mechanism that keeps the relay closed even if power to the relay is terminated. Hysteresis is essential to the workings of some memristors. Hysteresis can be used when connecting arrays of elements such as nanoelectronics, electrochrome cells and memory effect devices using passive matrix addressing. Shortcuts are made between adjacent components and the hysteresis helps to keep the components in a particular state while the other components change states. Thus, all rows can be addressed at the same time instead of individually. In the field of audio electronics, a noise gate often implements hysteresis intentionally to prevent the gate from chattering when signal close to its threshold are applied. User interface design. Hysteresis is sometimes intentionally added to computer algorithms. The field of user interface design has borrowed the term hysteresis to refer to times when the state of the user interface intentionally lags behind the apparent user input. For example, A menu that was drawn in response to a mouse over event may remain on screen for a brief moment after the mouse has moved out of the trigger region and the menu region. This allows the user to move the mouse directly to an item on the menu, even if part of the direct mouse path is outside of both the trigger region and the menu region. For instance, right-clicking on the desktop in most Windows interfaces will create a menu that exhibits this behavior. Aerodynamics. In aerodynamics, hysteresis can be observed when decreasing the angle of attack of a wing after stall. Regarding the lift and drag coefficients, the angle of attack where the flow on top of the wing reattaches is generally lower than the angle of attack where the flow separates during the increase of the angle of attack. In mechanics, elastic hysteresis. In the elastic hysteresis of rubber, the area in the center of a hysteresis loop is the energy dissipated due to material internal friction. Elastic hysteresis was one of the first types of hysteresis to be examined. A simple way to understand it is in terms of a rubber band with weights attached to it. If the top of a rubber band is hung on a hook and small weights are attached to the bottom of the band one at a time, it will get longer. As more weights are loaded onto it, the band will continue to extend because the force the weights are exerting on the band is increasing. When each weight is taken off or unloaded, the band will get shorter as the force is reduced. As the weights are taken off, each weight that produced a specific length as it was loaded onto the band now produces a slightly longer length as it is unloaded. This is because the band does not obey Hooke's law perfectly. The hysteresis loop of an idealized rubber band is shown in the figure. In terms of force, the rubber band was harder to stretch when it was being loaded than when it was being unloaded. In terms of time, when the band is unloaded, the effect lagged behind the cause because the length has not yet reached the value it had for the same weight during the loading part of the cycle. In terms of energy, more energy was required during the loading than the unloading, the excess energy being dissipated as heat. Elastic hysteresis is more pronounced when the loading and unloading is done quickly than when it is done slowly. Some materials such as hard metals don't show elastic hysteresis under a moderate load, whereas other hard materials like granite and marble do. Materials such as rubber exhibit a high degree of elastic hysteresis. When the intrinsic hysteresis of rubber is being measured, the material can be considered to behave like a gas. When a rubber band is stretched, it heats up, and if it is suddenly released, it cools down perceptibly. These effects correspond to a large hysteresis from the thermal exchange with the environment and a smaller hysteresis due to internal friction. Within the rubber, this proper intrinsic hysteresis can be measured only if the rubber band is adiabatically isolated. Small vehicle suspensions using rubber can achieve the dual function of springing and damping because rubber, unlike metal springs, has pronounced hysteresis and does not return all the absorbed compression energy on the rebound. Mountain bikes have made use of elastomer suspension, as did the original mini car. The primary cause of rolling resistance when a body rolls on a surface is hysteresis. This is attributed to the viscoelastic characteristics of the material of the rolling body. Contact angle hysteresis. The contact angle formed between a liquid and solid phase will exhibit a range of contact angles that are possible. There are two common methods for measuring this range of contact angles. The first method is referred to as the tilting base method. Once a drop is dispensed on the surface with the surface level, the surface is then tilted from 0 degrees to 90 degrees. As the drop is tilted, the downhill side will be in a state of imminent wetting while the uphill side will be in a state of imminent dewetting. As the tilt increases, the downhill contact angle will increase and represents the advancing contact angle, while the uphill side will decrease. This is the receding contact angle. The values for these angles just prior to the drop releasing will typically represent the advancing and receding contact angles. The difference between these two angles is the contact angle hysteresis. The second method is often referred to as the add-remove volume method. When the maximum liquid volume is removed from the drop without the interfacial area decreasing, the receding contact angle is thus measured. When volume is added to the maximum before the interfacial area increases, this is the advancing contact angle. As with the tilt method, the difference between the advancing and receding contact angles is the contact angle hysteresis. Most researchers prefer the tilt method. The add-remove method requires that a tip and needle stay embedded in the drop, which can affect the accuracy of the values, especially the receding contact angle. Adsorption hysteresis. Hysteresis can also occur during physical adsorption processes. In this type of hysteresis, the quantity adsorbed is different when gas is being added than it is when being removed. The specific causes of adsorption hysteresis are still an active area of research, but it is linked to differences in the nucleation and evaporation mechanisms inside mesopores. These mechanisms are further complicated by effects such as cavitation and pore blocking. In physical adsorption, hysteresis is evidence of mesoporosity. Ndthe. The definition of mesopores is associated with the appearance and disappearance of mesoporosity in nitrogen adsorption isotherms as a function of Kelvin radius. An adsorption isotherm showing hysteresis is said to be of type 4 or type 5, and hysteresis loops themselves are classified according to how symmetric the loop is. Adsorption hysteresis loops also have the unusual property that it is possible to scan within a hysteresis loop by reversing the direction of adsorption while on a point on the loop. The resulting scans are called crossing, converging, or returning, depending on the shape of the isotherm at this point. Metric potential hysteresis. The relationship between metric water potential and water content is the basis of the water retention curve. Metric potential measurements are converted to volumetric water content measurements based on a cytosol-specific calibration curve. Hysteresis is a source of water content measurement error. Metric potential hysteresis arises from differences in wetting behavior causing dry medium to re-wet. That is, it depends on the saturation history of the porous medium. Hysteretic behavior means that, for example, at a metric potential of 5 kilopascals, the volumetric water content of a fine sandy soil matrix could be anything between 8% to 25%. Tensiometers are directly influenced by this type of hysteresis. Two other types of sensors used to measure soil water metric potential are also influenced by hysteresis effects within the sensor itself. Resistance blocks, both nylon and gypsum-based, measure metric potential as a function of electrical resistance. The relation between the sensor's electrical resistance and sensor metric potential is hysteretic. Thermocouples measure metric potential as a function of heat dissipation. Hysteresis occurs because measured heat dissipation depends on sensor water content, and the sensor water content metric potential relationship is hysteretic. As of 2002, only desorption curves are usually measured during calibration of soil moisture sensors. Despite the fact that it can be a source of significant error, the sensor-specific effect of hysteresis is generally ignored. In materials, magnetic hysteresis. When an external magnetic field is applied to a ferromagnetic material such as iron, the atomic dipoles align themselves with it. Even when the field is removed, part of the alignment will be retained. The material has become magnetized. Once magnetized, the magnet will stay magnetized indefinitely. To demagnetize it requires heat or a magnetic field in the opposite direction. This is the effect that provides the element of memory in a hard disk drive. The relationship between field strength H and magnetization M is not linear in such materials. If a magnet is demagnetized and the relationship between H and M is plotted for increasing levels of field strength, M follows the initial magnetization curve. This curve increases rapidly at first and then approaches an asymptote called magnetic saturation. If the magnetic field is now reduced monotonically, M follows a different curve. At zero field strength, the magnetization is offset from the origin by an amount called the remanence. If the H-M relationship is plotted for all strengths of applied magnetic field, the result is a hysteresis loop called the main loop. The width of the middle section is twice the coercivity of the material. A closer look to magnetization curve generally reveals a series of small, random jumps in magnetization called Barkhausen jumps. This effect is due to crystallographic defects such as dislocations. Magnetic hysteresis loops are not exclusive to materials with ferromagnetic ordering. Other magnetic orderings, such as spin glass ordering, also exhibit this phenomena. Physical origin. The phenomenon of hysteresis in ferromagnetic materials is the result of two effects: rotation of magnetization and changes in size and number of magnetic domains. In general, the magnetization varies across a magnet, but in sufficiently small magnets, it does not. In these single-domain magnets, the magnetization responds to a magnetic field by rotating. Single-domain magnets are used wherever a strong, stable magnetization is needed. Larger magnets are divided into regions called domains. Across each domain, the magnetization does not vary, but between domains are relatively thin domain walls in which the direction of magnetization rotates from the direction of one domain to another. If the magnetic field changes, the walls move, changing the relative sizes of the domains. Because the domains are not magnetized in the same direction, the magnetic moment per unit volume is smaller than it would be in a single domain magnet, but domain walls involve rotation of only a small part of the magnetization, so it is much easier to change the magnetic moment. The magnetization can also change by addition or subtraction of domains. Magnetic hysteresis models. The most known empirical models in hysteresis are Pryzak and Giles Atherton models. These models allow an accurate modeling of the hysteresis loop and are widely used in the industry. However, these models lose the connection with thermodynamics and the energy consistency is not ensured. Last models rely on a consistent thermodynamic formulation. Ndthe model is inspired by the kinematic hardening laws and by the thermodynamics of irreversible processes. In particular, in addition to provide an accurate modeling, the stored magnetic energy and the dissipated energy are known at all times. The obtained incremental formulation is variationally consistent, i.e., all internal variables follow from the minimization of a thermodynamic potential. That allows to obtain easily a vectorial model, while Pryzak and Giles Atherton are fundamentally scalar models. Applications. There are a great variety of applications of the hysteresis in ferromagnets. Many of these make use of their ability to retain a memory, for example magnetic tape, hard disks, and credit cards. In these applications, hard magnets like iron are desirable so the memory is not easily erased. Soft magnets are used as cores in electromagnets. The nonlinear response of the magnetic moment to a magnetic field boosts the response of the coil wrapped around it. The low coercivity reduces that energy loss associated with hysteresis. Electrical hysteresis. Electrical hysteresis typically occurs in ferroelectric material, where domains of polarization contribute to the total polarization. Polarization is the electrical dipole moment. The mechanism and organization of the polarization into domains is similar to that of magnetic hysteresis. Liquid-solid phase transitions. Hysteresis manifests itself in state transitions when melting temperature and freezing temperature do not agree. For example, agar melts at 85 degrees Celsius and solidifies from 32 to 40 degrees Celsius. This is to say that once agar is melted at 85 degrees Celsius, it retains a liquid state until cooled to 40 degrees Celsius. Therefore, from the temperatures of 40 to 85 degrees Celsius, agar can be either solid or liquid, depending on which state it was before. In biology, cell biology and genetics, cells undergoing cell division exhibit hysteresis in that it takes a higher concentration of cyclones to switch them from G2 phase into mitosis than to stay in mitosis once begun. Darlington in his classic works on genetics discussed hysteresis of the chromosomes, by which he meant failure of the external form of the chromosomes to respond immediately to the internal stresses due to changes in their molecular spiral, as they lie in a somewhat rigid medium in the limited space of the cell nucleus. In developmental biology, cell type diversity is regulated by long-range acting signaling molecules called morphogens that pattern uniform pools of cells in a concentration and time-dependent manner. The morphogen sonic hedgehog, for example, acts on limbic neural progenitors to induce expression of a set of homeodomain containing transcription factors to subdivide these tissues into distinct domains. It has been shown that these tissues have a memory of previous exposure to SHH. In neural tissue, this hysteresis is regulated by a homeodomain feedback circuit that amplifies SHH signaling. In this circuit, expression of GLI transcription factors, the executors of the SHH pathway, is suppressed. GLIs are processed to repressor forms in the absence of SHH, but in the presence of SHH, a proportion of GLIs are maintained as full-length proteins allowed to translocate to the nucleus, where they act as activators of transcription. By reducing GLI expression then, the HD transcription factors reduce the total amount of GLI, so a higher proportion of GLI can be stabilized as GLI for the same concentration of SHH. Immunology. There is some evidence that T cells exhibit hysteresis in that it takes a lower signal threshold to activate T cells that have been previously activated. RAS activation is required for downstream effector functions of activated T cells. Triggering of the T cell receptor induces high levels of RAS activation, which results in higher levels of GTP-bound RAS at the cell surface. Since higher levels of active RAS have accumulated at the cell surface in T cells that have been previously stimulated by strong engagement of the T cell receptor, weaker subsequent T cell receptive signals received shortly afterwards will deliver the same level of activation due to the presence of higher levels of already activated RAS as compared to a naive cell. Neuroscience. The property by which some neurons do not return to the basal conditions from a stimulated condition immediately after removal of the stimulus is an example of hysteresis. Respiratory physiology. Lung hysteresis is evident when observing the compliance of a lung on inspiration versus expiration. The difference in compliance is due to the additional energy required during inspiration to recruit and inflate additional alveoli. The transpulmonary pressure versus volume curve of inhalation is different from the pressure versus volume curve of exhalation, the difference being described as hysteresis. Lung volume at any given pressure during inhalation is less than the lung volume at any given pressure during exhalation. Voice and speech physiology. A hysteresis effect may be observed in voicing onset versus offset. The threshold value of the subglottal pressure required to start the vocal fold vibration is lower than the threshold value at which the vibration stops, when other parameters are kept constant. In utterances of vowel voiceless consonant vowel sequences during speech, the intraoral pressure is lower at the voice onset of the second vowel compared to the voice offset of the first vowel. The oral airflow is lower, the transglottal pressure is larger and the glottal width is smaller. Ecology and epidemiology. Hysteresis is a commonly encountered phenomenon in ecology and epidemiology, where the observed equilibrium of a system cannot be predicted solely based on environmental variables, but also requires knowledge of the system's past history. Notable examples include the theory of spruce budworm outbreaks and behavioral effects on disease transmission. In economics, economic systems can exhibit hysteresis. For example, export performance is subject to strong hysteresis effects. Because of the fixed transportation costs, it may take a big push to start a country's exports, but once the transition is made, not much may be required to keep them going. When some negative shock reduces employment in a company or industry, fewer employed workers then remain. Usually the employed workers have the power to set wages. The reduced number incentivizes them to bargain for even higher wages when the economy again gets better, instead of letting the wage be at the equilibrium wage level, where the supply and demand of workers would match. This causes hysteresis. The unemployment becomes permanently higher after negative shocks. Permanently higher unemployment. The idea of hysteresis is used extensively in the area of labor economics, specifically with reference to the unemployment rate. According to theories based on hysteresis, severe economic downturns and/or persistent stagnation cause unemployed individuals to lose the job skills that find them, become obsolete, or become demotivated, disillusioned, depressed, to lose job-seeking skills. In addition, employers may use time spent in unemployment as a screening tool, i.e., to weed out less desired employees in hiring decisions. Then, in times of an economic upturn, recovery, or boom, the affected workers will not share in the prosperity, remaining unemployed for long periods. This makes unemployment structural, i.e., extremely difficult to reduce simply by increasing the aggregate demand for products and labor without causing increased inflation. That is, it is possible that a ratchet effect in unemployment rates exists, so a short-term rise in unemployment rates tend to persist. For example, traditional anti-inflationary policy leads to a permanently higher natural rate of unemployment. This occurs first because inflationary expectations are sticky downward due to wage and price rigidities, and second because labor markets do not clear instantly in response to unemployment. The existence of hysteresis has been put forward as a possible explanation for the persistently high unemployment of many economies in the 1990s. Hysteresis has been invoked by Olivier Blanchard among others to explain the differences in long-run unemployment rates between Europe and the United States. Labor market reform. A strong demand-side economic growth may not therefore reduce this pool of long-term unemployed. Thus, specific targeted training programs are presented as a possible policy solution. However, the hysteresis hypothesis suggests such training programs are aided by a persistently high demand for products, which reduces the transition costs out of unemployment and into paid employment easier. Game theory. Hysteresis occurs in applications of game theory to economics, in models with product quality, agent honesty or corruption of various institutions. Slightly different initial conditions can lead to opposite outcomes and resulting stable good and bad equilibria.